So let's talk about significant figures. First, why do we need significant figures in the first place? And the answer is, when you measure something, the degree to the precision to which you know that number depends on several factors, but ultimately that precision needs to be communicated, right? Let's say I measure the width of a desk, right? And I measure it to be 2 feet. Well, is that exactly 2 feet? Is that two feet good to like a quarter inch? Is that 2 feet good to, a hair's width? Because if you were gonna make a new, let's see, tabletop for that desk, you wouldn't want to know like how accurate, how really precise, I should say, how precise is that 2 feet? So how many decimals you include after that? So we could say 2 feet. Actually, let's go back to, I've got some scratch paper over here. Nope. Almost. Okay. Thank you for your patience. Okay, so we're saying 2 feet versus 2 feet. Do you see the difference? Right? The 2 feet on the left, you can't really say if it's 2 feet plus or minus an inch, plus or minus several inches, but 2 feet on the right, you can definitely say like, oh, that's not more than an inch off. So this is a little hard to say because how much of a foot is an inch? Well, it's 1/12. This is definitely not an inch off though, because 1/12 is a little smaller than 0.1. This is definitely better than that. So let's switch to SI units. Make that go away a little bit. Okay, great. So same sort of thing. I can say for time, I could say 12.3 seconds or 12.300 seconds. So one of them has more significant figures, and it's because it's more precise, right? It's closer to true 12.3 than the other one is. Or at least we're stating with more confidence how close it is to 12.3. So that means these two zeros are significant. Right? So that leads to one of these rules, which is unnecessary zeros are significant. Does that make sense? That sounds backwards, but these zeros didn't have to be here to tell me it was 12.3. Those zeros are there specifically to tell me how precise this number is. That's why those are significant. Whereas if I had, let's not do 100. Let's do 105. That zero is also significant, right? Because it's telling me exactly how many tens there are in that 105. There are 0 tens, exactly 0 tens. Whereas if I go like this, so I'll say significant. Any number that's not 0 is automatically significant. It's automatically telling me something. So the trick is there are some zeros that are not significant. They're there to tell me where the decimal is. So I could do like this. It's really leading zeros. 0.0015. These 3 zeros, they're necessary, and so they are insignificant. Those 3 zeros are insignificant because they're telling me that they have to be there to show me where the decimal point is. So we'll just say not significant. But if I added a 0 to the end, that 0 is unnecessary, that 0 is significant. Okay, so at some point, some examples are just going to be the easiest thing to do. So let's do some examples. Let's make my 2 feet go away. Okay, so how many sig figs are there in these numbers? Well, again, any number that's not a 0 is significant. So this one has, we can zoom in a little, oops. Oh, come on. This one has 3, right? 1, 2, 3. So that's 3 sig figs. And you see, sig fig is so much easier to say than significant figures, even if it sounds a little irritating. Okay, so what else? The next number. Well, the next number is the same number-ish, but the decimals moved, right? But all the digits there are non-zero, so it's still 3 sig figs. Okay, yeah, this is okay. This is fine. The next number's got 2 zeros in it. Well, the leading zero is just to clarify where the decimal point is, so that leading zero is not significant. So I'm going to do this. And these other numbers, so that's definitely a sig fig, that's definitely a sig fig, and that zero didn't need to be there. So it's there intentionally. It's there to tell me how well or how close to 0.62 this number is. So this has 3 sig figs. Even though there are 4 digits there, only 3 of them are significant. Okay, so here's another number, 6.2. Well, there's 1, there's 2, and this 10 to the minus 2 is also telling me where the decimal is. So 10 to the minus 2 does not add to the sig figs, right? It's just this thing. So this is 2 sig figs. All right, again, the non-zero digits are significant, and digits that are only there to tell me where the decimal is, they are not significant. That's why that 10 to the minus 2 is not significant. Okay, so letter E is literally the same number, right? 6.2 times 10 to the minus 2, which would be, if we're keeping track, that would be 0. So we move that decimal 2 places. So 0, 6, 2. Okay. So letter E is the same number, but look, it's got an extra 0 in it, and that extra 0 is not showing me where the decimal is, right? So it is significant. That's 3 sig figs. Okay, and we're almost there. Okay. 6,200. 6,200. Okay. Well, those 2 zeros, we've talked about leading zeros being insignificant or not significant. Trailing zeros sometimes are, but those 2 zeros have to be there. If those zeros aren't there, how do you say that this is 6,200? So those 2 zeros are not significant. There is a way you could put a decimal at the end, and sometimes that signifies that it's significant. We'll say 2 sig figs. Deviating from my color scheme. It's okay. One way to say those zeros do not matter very, very clearly is to write it in scientific notation, right? 6.2 times 10 to the 2. Now you don't have to put those zeros. This is a lot clearer than this. All right, so scientific notation is useful for sig fig communication. It's also useful when you have really big or really small numbers. It keeps you from having to use a whole bunch of zeros to show where the decimal is. Okay, great. What else can we do with sig figs? Well, again, sig figs are just telling us how precise a number is. And one thing we can do with numbers is put them together mathematically. So let's talk about these 2 rules. Nope, I just want my scratch paper. Okay, so let's talk about addition and subtraction. When you add or subtract numbers, the precision of those numbers matters. All right, so the rule is the number that is least precise dictates the precision of the answer. All right, it's a lot like saying the example I said before. Let's say I've got a desk, right? It's a 2-foot desk, and I'm we'll do it this way. So 2 feet plus, and let's say that's exactly how I know it, plus another little bit. So I'm maybe butting this up against another piece of furniture, and there's this much space between the furniture, and then another couple inches, right? Plus 2 inches. Well, I'm going to have to convert that 2 inches to feet for this to be reasonable. But if this is as well as I know this, as precise as I know the width of the desk, the answer is still pretty much 2 feet. Do you see? The least precise thing, the least precise number, governs the precision of the answer. Okay, so that seems like a kind of hand-wavy thing. Let's do a more concrete example. All right, so let's just make it up. No, let's not make it up because I don't trust my mental math. So let's go back to this. Down here. Here. Okay. So 2.67 plus 1.976 plus 2.1. So you remember when you learned how to add numbers with decimals? You line up the decimals vertically. This actually exemplifies this very well. So 2.67 plus 1.976 plus 2.1. So you see the least precise number ends at the 10th spot. That means the 7, 6, this 7, 6, and this 7 aren't going to affect the precision of the answer. I'm going to add them with that so that there can be some carryover digits, but I'm going to drop them ultimately. All right, so when you do this addition, you get 6.746. 6.746, right? The 6 dropped down. The 7 and the 7 is a 14, so that carried a 1, and then you add all those. So there's a 6, a 1, a 9, and 1, so that's 10 and a 17, right? So you carried the 1. 1, 2, 3, 4, 5, 6. Oh, great. We can add. But again, the least precise number stopped right here, so I'm going to cut it off there. So my answer is 6.7, and there are no units. So the least precise number in addition governs the precision of the answer. Okay, so same sort of thing here in letter B. 1,299 grams plus 45.1 kilograms. And I'm supposed to answer this in milligrams, which is obnoxious, but we can do it. So to add these numbers, they need to have the same units. And something I should have mentioned, to add these numbers, they really do need to have the same units. They also need to be the same type of unit, right? I could say, what's 5 meters plus 3 seconds? Well, that does not compute, right? You can't do that. But 5 meters plus 3 centimeters, I can do that, but I'm going to have to convert. Same thing here. All right, so let's convert them, I don't know. Frankly, we could convert them both to milligrams to start. Let's do that. Why not? Okay, so how do I convert this to milligrams? Well, 1299 grams times milli is 10 to the minus 3, so I want milligrams to show up and grams to go away. So 1 gram is 10 to the 3 milligrams, right? So that's 1, 2, 9, 9, and 3 more zeros milligrams. Or I could write this, because that's obnoxious. I could write this as 1 point, oops, I said 1 and I wrote a 2. Let's do this. I could say 1.299 times 10 to the 6 milligrams. Not sure why we're expressing this in milligrams, but that is okay. We do what we are asked. 45.1 kilograms times, and I want to get the milligrams. You may have learned as a student in science before now. How to write out the you could write the base units, right? And you can go what deca, hecta, killa, and then down deci, centi, milli. So you can count from K to M, 1, 2, 3, 4, 5, 6. You can do that. It breaks down when you try to go further, though, right? So from killi, the next one doesn't have a name, and the next one doesn't have a name, but the one after that is mega, and the next one doesn't have a name, and the next one doesn't have a name, but the one after that is oh, it escapes me. You know what? I've got it over here. Giga, right? And then tera. Same thing here. If you go back the other way, so milli and so once you go smaller than milli, there is no number for 10 to the minus 4, 10 to the minus 5, or no name. But 10 to the minus 6 is micro, and then 10 to the minus 9 is nano, and pico, and femto. My field is nanoscience, so I know the smaller ones a lot better than the bigger ones, which is why giga slipped my mind. So what I'm saying is this. If you have done... Oh, come on. If you have done this in the past, this thing right here, that is okay. It's just not going to work when you go bigger than kilo or smaller than milli. All right, just for your information. Okay. That was a fun aside. So I would like kilograms to go away and milligrams to show up, but I can just stepwise this. So I can go from kilograms to grams. There's 1,000 grams in a kilogram. You might be able to do this without the intermediate steps. Now I want grams to go away and milligrams to show up. And again, there's 1,000 milligrams per gram. So that's 1,000 twice, which is 45.1 times 10 to the 6 milligrams. Right? 1,000. There's 10 to the 3 and another 10 to the 3. That's 10 to the 6. Okay, that works out. Okay, what was I doing? I was adding. So let's add these two. 45.1 plus 1.299. Let's do that. 1.299 and 45.1. Looks like 993 and a 46. But the 45.1 is going to govern our Sig Figs. So I'm going to round that up, 46.4. And I could leave it in scientific notation if I want. 46.4 milligrams. I need the 10 to the... Come on now. Times 10 to the 6 milligrams. Okay, fabulous. So addition. That covers addition. What about multiplication? Multiplication, honestly, is something we do more often than addition and subtraction. By the way, subtraction follows the same rule as addition. Division and multiplication follow the same rule as well. It's a different rule, but it is the same for each. And you may have seen this before. There is a way to prove this. So what I showed you for addition and subtraction kind of makes gut sense, right? Has to do with precision. For multiplication and addition, you keep the... There's not a concise way to say it. Let's do this. Let's just do 12 times 143. Right? Of course, I chose numbers I can't do in my head. So what does that turn out to be? 12 times 143. 1,716. But this 12 only had 2 sig figs. So this has 2. This has 3. So I'm going to keep 2 sig figs. That's what I keep. So my answer is 1,700. All right. So you just keep whichever pre-number. There's got to be a word for that. Whichever number going into it has the fewest sig figs, that governs the sig figs for the answer. There is a way to show that, but I don't want to take the time to do it right now. So if you're interested, ask me, and we'll talk about it. But I don't want to do it right now. So let's just do some examples, because they're pretty quick. Also, I'm going to clear myself some space. Isn't this magical? So magical. Okay, so we can do this math. If you do this math right, so you just plug it into your calculator, you get 0.910811. And I'm sure that keeps going. But look, that has 2 sig figs, so that's where we're stopping. All right, so 0.91, boom, that's it. And so we can do this other one, 12.56 times 2.12. If you do that, you get 26.6272. 6272. And I'm sure that keeps going. I didn't do it right now, but I have done it in the past. And this guy has 3 sig figs, so that's what we're going to keep. So that is 26.6, and there's my answer. All right, so this is good guidance for how many sig figs to keep when you don't know where these numbers come from. In a laboratory setting, you would actually use you would propagate error, but we'll talk about that in the lab. I think that's actually more useful than sig figs, but if you don't have error to guide you, sig figs are a wonderful way to decide how many digits should I keep when I plug numbers into my calculator.